All right. Hello. After the lunch break to the first C++ talk today. My name is Andreas Fertig. I work as a software developer, as a trainer and speaker. I also happen to be the creator of C++ Insights, even that it's really hard for me to see you. So if everyone storms out before this presentation is over, please give me a heads up because I can barely see you. But let's try this anyway. Who here, by a show of hands, has heard of C++ Insights? Oh, that's fantastic. Okay, another question. Who has heard of Compiler Explorer from Matt Godbold? Excellent. All right. For all those who have not heard of C++ Insights, I will introduce it to you. Topic of today is C++ and Lambdas Demystified. So we are talking about a language. And because we are talking about a language, I like to take the opportunity to talk a little bit about a different language, about the German language, in particular my name. My last name is Fertig. And this is a meaningful word in German because it's an adjective, and translated to English, it roughly means something like finished, ready, complete, or completed. This is an excellent name to be in someone's team because everybody thinks then the team is always finished. It's not true, but they try. It's also a fortunate fact that in German it's an adjective, and then as an adjective it's spelled with a lower f at the beginning. However, as a name it's spelled with a capital F. So I'm constantly fighting with the spell checker which version is the right one. And so far we cannot agree. I'm telling this story about my name now for a couple of times, and every time I can add another piece to it. So I know that it's also a term known in Yiddish. The sadder part about my own name is that for roughly 30 years, I mispronounced my own name. All right? I'm still today not able to pronounce it the right way, at least in proper German, because in proper German it is pronounced Fertig, with h at the end. Due to my hometown where I come from, it's a hard G or K at the end, so I say Fertig. Well, there is no such word in German, so everybody gets what I'm telling. So, but back to C++ and Lambdas. This is a chart illustrating the evolution of Lambdas. It goes through all the standards, and from left to the right, we have the capture list. And in C++ 11, we were able to capture by copy, by reference, by named copy, by named reference. We were able to capture this, and of course, packs, parameter packs. With C++ 11, we got something like init capture, so we can introduce a new name from a captured variable. We will look into this later. Again, by copy or by reference. With C++ 17, we got the ability to capture something which is written *this. We will also look into this. Next to the capture list, with C++ 20, if my class bowl is right, we will have the angle brackets, and in that angle brackets we can write something like type name. So we will have templated lambdas in C++ 20. I will show you a couple of examples for that. Next, in parentheses, we have the parameter the lambda itself takes. With C++ 11, we can pass in a type like int or our own type, class, whatsoever. With C++ 14, we got generic lambdas, and now we can say auto at this place. This is the only place where we can say auto in a parameter list so far. Next to this, we have the specifiers with C++ 11, mutable, to tell that the lambda is capable of changing the values captured. With C++ 17, we got const expr, so lambdas are implicitly const expr there. I will show you examples for that. And with C++ 20, we will get const eval. And as I'm not a native speaker, I'm still unsure if I'm pronounced this right, because it's not evil, its evaluation at compile time. It's a little bit different than const expr. It has more guarantees. Next, we can have the acceptance specification with no accept, and with C++20 in the angle brackets, we will have expects and ensures coming from contracts. So we can also apply contracts to our lambdas. Then there is the optional trailing return type in case we like, or we have to specify the return type of the lambda. We can say int there or any arbitrary type we like. And with C++20, as concepts will be in C++20, there is now a requires clause, so we can apply concepts to lambdas in C++20. Then in the curly braces below, there is the body of the lambda, and after that, in the parentheses, there go the actual parameters if you invoke the lambda, either directly or later. So that's a brief overview about lambdas, and with that overview, I believe you can see that lambdas are constantly changed from standard to standard. So they are under active development, I would say. Now we are talking about active development. Have a look at this piece of code. And my question to you is, and I try to see you, but you can shout it out, is this valid or not in C++? Any guesses? Valid in 20. So the correct answer would be, it depends. It is valid in 20 so far. I read a mail on the WG21 mailing list that they are thinking about disallowing this. So what it essentially does is it declares a default constructible empty lambda, which is then default initialized. Of course, what else? So let's go to the Lambdas internals. Here I have a more meaningful code example. I have a const char string array which contains the string hello NDC Oslo. And then I have a lambda which captures this string and takes care of printing it out. All right? So far, nothing special. Now, let's peek behind the scenes. What's going on there? So for all those who are new to C++ Insights, this is C++ Insights. This is a website you can go to. On the left, you can enter the source code in C++ you like to get more knowledge about it. And then, if you hit the run button, you get on the right an enriched version, enriched by what the compiler does for us internally or adds to our code to make it compile. You will see, for example, implicit conversion, template instantiation, and all that kind of things. For our example here now, we can see how a lambda works. This here is the lambda from the internal view of the compiler. What the compiler generates from us, from the code on the left, is essentially a class. It's, from standards perspective, either a class or a struct. The tool is powered by Clang, and Clang choose to make it a class. So here it is a class, and it has one specialty, and this is the call operator. And the call operator is the thing we invoke or call if we call or invoke our lambda. So essentially, we are able to write lambdas in C++ 98. So it's nothing new. It's a class, it's a call operator, both have been there in C++ 98. But with C++ 11, the compiler is now able to transform this small and nice version of code into this internal version. So internally, it's just syntactic sugar. The compiler also takes care, of course, of the captures we are requesting. So there are members of the class. In this case, I have a reference to an array of size 15 here, which is the string hello NDC Oslo. In this call operator, I have the body from my lambda, nice and easy. And later on, as you can see, the call operator invokes this lambda. So this is the basics about lambdas. Internally, they are classes, they have members, and the compiler just transforms this for us. If you have any questions, feel free to ask them now or later. I have a question for you. While developing C++ in Sites, I tried carefully to find places where lambdas can appear such that I can see that my transformation is correct. And once I stumbled over this example, and it made me think, in how many places can lambdas appear there? And it doesn't mean that it has to be meaningful or code you daily write. It's just a question, where in this piece of code can lambdas appear? Just give me a number. We are not talking about recursive lambdas. Would be another story. Any guesses? One. One is correct, but not enough. 4 is close. It's 5. Yeah, 5 is the correct answer. Nice. Unlimited would be a nice different answer. But I take 5 here, and the 5 places are, I can use a lambda to initialize x. Not really meaningful, but I can do it. I will show an example later which has more meaning to it. I can use it in the for loop in the initializing part to print out something like started. Then, of course, I can use it again in the for loop for comparing or evaluating if the for loop has to end. So there I can decrement x and invoke the lambda directly, of course. And then I can do in the last part of the for loop, do another printf so that after each loop iteration, it prints out after. And of course, I can wrap this whole printf in a lambda to invoke it. So lambdas essentially can appear everywhere where an expression can appear. Yes?
In the printf, can you replace x with a lambda and then print it as a function address?
Yes, that would be possible as well. So that was the case before. As the printf takes a variable number of arguments, in theory, the number would be probably not infinite because the compiler has a limit, I believe, but a large number. Yeah. Let's talk a little bit about capturing, and in this case, capturing global variables. This is the code from the slide. So what I have here is I have a global variable x, I have my main function, and I have a lambda here which increments x. And sometimes when I show this example, I get 2 responses. One is this code does not compile because the lambda does not capture anything. There is neither capture by copy nor capture by reference. And in addition, the lambda is not able to increment x because it's not mutable. And this is partially true, because it would be true if it's not a global variable. But for a global variable is always there. It's reachable, so there is no need to capture it. And as the compiler is a good friend of us, it does the best it can do for us. So if we transform this, we can see there is no member x. And by the way, if I can transform the code, it means that it compiles. Also, there's a little output here saying that it compiles. So this is totally valid code. And First of all, I think it's great that we do not have to worry that things are captured without the need. But on the other hand, sometimes it can be the case that we like to capture X to preserve the state from the past or something like this. So, and if it comes to such a case for global variables, we can use init captures. I will show you later what init captures are. Questions to that so far? All right.
One question.
Yes.
Is it specified by standard that lambdas should convert to objects or classes, or might they be converted to something else as well?
It's specified that a lambda is either a class or a struct. I'm not sure if you're hinting to something a little bit more special, so I would say I'm not sure. Let's talk about this later. Bless you. So, if we have captureless lambdas, as before in the example of capturing a global variable, we can also assign them to ordinary function pointers coming from C, which is nice if we have to deal with legacy API or C API where we cannot pass classes in or something like this. So in this case, I initialize my function pointer fp with a lambda which captures nothing. It just returns a plus b. And if you look in C++ inside what's happening there, this is the code from the slide, and if I transform it, we can see that in this case I have two additional methods. One is called Invoke. The name is free to choose from the implementation. And this Invoke has the same body as our lambdas body. Of course, I have the call operator, and then I have this method here, which is called the conversion operator. And it ensures that it returns this invoke function such that this lambda is assignable to this function pointer because of this conversion operator. So it's a static member function, and because this is a captureless lambda, it only works for captureless lambdas. It doesn't have the need to use anything from the class because there are no members, so it can just return the static member function. This is how it works, assigning lambdas to function pointers. I'm working mostly in the embedded domain, this domain where size matters, and despite what you may read in the internet for different things, the small size matters more than the larger one often. So I care about size, and my question is, I have this code here. I have int main, I have three variables a, b, and c being of type char, while b is of type int. And then I have my lambda f, which captures everything by copy, and I just use a, b, and c inside of the lambda. Declaring or using them with a semicolon is enough for the lambda to capture them. For the following question, assume that we are talking about an x64-bit platform. And the question is, what is the size of this lambda if you would apply a size off to it? Neither 10 nor 24, no. 10 is closer. 12. It's 12. Because when we are talking about an x64-bit platform, our int is roughly 4 bytes or 8 bytes, 4 bytes of size, and if you then add the two chars, which are of 1 byte, we would be having 6 bytes, but due to the alignment rules, we are getting up to 12. So we are essentially, from my perspective, wasting bytes. It's not what I like. What can we do? Have you seen the change? This is the original version, this is the changed version. All I did, I changed the order I used the variables in my lambda. Instead of having it A, B, and C, it's now A, C, and B. With that, I'm able to reordering the captures. And as with every struct, the order of the variables makes the size, if you like. So with changing it like this, I get down to 8 bytes. So I just saved 4 bytes, which is great. However, let's talk a little bit about the standard. So what the standard says here is, an implementation may define the closure type differently from what it is described below, provided this does not alter the observable behavior of the program other than the size and/or alignment of the closure type. So what I've just shown you is technically undefined behavior. It works currently in all the major compilers. If they are getting smarter with lambdas, maybe at some point they are able to do this little trick for us and reducing the size automatically. As of today, I'm not aware that they are doing this. So, but be aware, it's technically not the best idea, at least not without knowing that it's undefined. Björn?
Can you change the size by explicitly capturing by value in a specific order?
If you're using init captures, then it's the same thing. To my knowledge, today compilers just take the variables as they are used. So if you're doing it with the init captures, it's the same. They are then going through the init captures and making up the fields of the class. And from my reading, they would be able to change this as well, because we are practically observing the size and the alignment of the lambda. So they are allowed to change this later, even for init captures, I believe. But that would be the better way, because not always you are free to choose in the body of the lambda where you use the variables or when. Let's switch to C++ 14 and look into generic lambdas. Generic lambdas are lambdas which have auto in their parameter list. This allows us to write even more generic code, because now we do not have to say our lambda type takes an int or a float. We can just say it takes something, a type, auto. And if you look at how generic lambdas are implemented, once again, this is the code from the slides. And if I transform this, you can see this piece of code here, which is again the call operator, but this time with the template keyword in front of it. So this time we are looking at an operator template. This is how auto works. If you are writing auto for a generic lambda, the call operator becomes a template. And with that, we're down to the basic rules we know for templates. So all this was added just with a compiler writers may not agree to this, but just with a little change to the parsing and then generating the syntactic sugar after it, making it classic C++ code. With that knowledge, we can think a little bit about what we can do with that. And if we are having C++ 17 on our hands, we can now say, well, as we now know that every parameter in a generic lambda we declared with auto is essentially a template parameter, we can apply const exprif and decal type to it to say in the body of the lambda, well, let's check if our type, which is passed in, is of type double. If so, let's multiply v by times 2.0. And in all other cases, just multiply it with 2. You can do other things to that, but it's one thing you can do with const per if because you need a template parameter for const per if. There's another thing I call the dangling reference trap, and I believe most of you probably have heard of this or have seen of this or have bitten by it. So what I have here is a function func which has an int in it, int x, which is initialized with 22, and it has a lambda L which captures by reference, and it returns x times x. And then there follows a bunch of code I'm not showing you here, and then I return this lambda. Is this all right? X is on the stack, correct. So the moment I return this lambda, it internally points to something on the stack which is no longer valid. So pointing to something on the stack which is no longer valid is technically undefined behavior. So you shouldn't do that. And for the talk, I looked it up in the standard. And this may be my famous quote or my most famous quote so far. So what the standard says, if a non-reference entity is implicitly or explicitly captured by reference, invoking the function call operator of the corresponding lambda expression after the lifetime of the entity has ended is likely to result in undefined behavior. Isn't that nice? One thing of undefined behavior is that we don't know if it works for the right reason or not. So it can work, but it can stop in the future. What does now mean likely undefined behavior? If it works, it's all right. I don't know where this word comes from and why is it there, but it's funny. So to fix this code, of course, the fix is very simple. Instead of capturing by reference, we capture by copy and we return that thing and everything is fine. Nice and easy. This is the fix you normally get if you show this code and ask anybody to fix it. And then you happen to have a new colleague, male or female, and he or she has to change that code. And due to that course, applied to the bunch of code that follows, my int now becomes an int pointer. It's allocated with new and initialized as before, and then the lambda is also adjusted, so now it is a dereferenced version of x times x, everything as before, and then I return it, nice and easy. Do you see the problem? It's a memory leak, so somebody came up with that. It's a memory leak, so of course we need to add a delete statement here. Oh boy. Yeah, it was partially okay, but now I'm still returning or again returning something which is no longer valid because it's deleted. So to make it right, a shared pointer would be appropriate here. It's not always that easy to say that if you capture by copy, you're safe. Okay, that's the point here. Let's talk a little bit more about captures. Here's an example. I have a class test which has a constructor, takes one argument, int x, and it has a member a, also of type int. And in that constructor's body, I have a lambda L1, which captures by copy and returns a plus 2. So a is the member of test. Then I invoke this lambda and print the result out. Just because I can, I increment a by 1 and I do the printing again. What's the output of the two printfs? And let me make this easy for you. 2 times 2 is 4. Okay? As we are right after lunch break. What's the output? Twice 4. Everybody agrees with twice 4. Someone objects to it? I do. Of course, the output is 4 and 5. And why is that? It's because when I say capture by copy, and I capture a member of a class, internally it captures the this pointer by copy. And that this is a pointer. I just have a pointer inside my lambda pointing to the this pointer. And this is why I'm seeing the effect that A is incremented. So if I say capture by copy in a class, it captures the this pointer. I can fix this in C++ 17 by saying I like to capture dereferenced this, or star this, however you like to read it. And that means that now a real copy of this, a deep copy of this is captured. And if I now print this out again, as you can see, the output is 4 and 4, so twice 4, as you expected before. As I said, I care about size. I've now shown you a version to fix this problem. This is a reduced version. I'm still capturing A and returning it, just with a little bit less boilerplate code. The thing is, what does this lambda capture now? And if we look at this in C++ insights, if I transform this, you can now see, of course, as I said, it's capturing a copy of test. So a copy of the this pointer. But this also means that now I do not capture just A as requested. No, I'm capturing A and B. So the size of my lambda is now the size of test, which is maybe not what I wanted, because I specifically requested A and I do not use anything else than A. I can fix this by using so-called init captures. This is this part. Init captures came in with C++ 14, and there I can now say that I like to capture the variable A by copy and give it a new name internally in the lambda A1. I use A1 here to make it less confusing. I can also say A. Doesn't matter. And now there's the question.
Yes, it's not about this. It's on the
before.
Capture star this technicality. I was just wondering, is it strictly okay to capture star this in the constructor, because the test object doesn't really exist until the constructor has finished the execution?
Probably you're right. It's not okay. Yeah, you're right. I checked that. Yes?
Does capturing by star this invoke the copy constructor? Like, is it a copy of the...
Yeah, it would be a deep copy of this. So it's one reason why it's not always probably okay, because if my this has a, I don't know, a large std string, a megabyte or so, then I'm capturing this and copying it in the lambda without even referring to it. So that's why the init captures are better if you care for the size and for your resources, because now you can see, okay, it's just capturing the int I did like to capture. And as I said, I can remove the A1 and can just say it's A. That's fine as well. It's up to you to decide which one is more readable for you, having two variables with the name A or giving the one another name. Still talking about the size of lambda. Here's one more example. maybe still undefined behavior because I'm doing it in the constructor. There's a little change now. My constructor has a const int variable named size, which is initialized with 2. And then I have my lambda L2, which again captures by copy. And aside from, as before, returning a plus 2, it now declares an int array, name x in it, and initializes it with the default. And the size of this array comes from the variable size. So my question is, does this increase the size of the lambda? Does this add another capture size to lambda? Guesses? You don't think so because it's const. Let's see. So far, you're right. It's not captured in the lambda because it's not ODR used, so the one definition rule, so it doesn't need to be captured here. So it's once again a case where the compiler, if you are caring about the size, is a good friend, and what does not need to be captured is not captured here. So it's a special case because it's not ODR used. If I would have used it for other things in the lambda, it would have been captured. A plus size, for example, yeah. So, like this. No, I'm wrong. It's still const, so it's still under the ODR rules. My apologies. Here's one more example. I give you a complete example. It's the function main. It had a std string in it with the name foo. And then I have a couple of lambdas a to f, which all capture either by reference, by copy, by named copy or so. And some of them do printf the value of foo. If you look closely at this example, you can see that none of these lambdas is invoked. Right? They are just there. They are practically unused. The question to you is, how many unused variables will I get from a compiler? Just yell out a number. Or the time I heard. Probably all versions. Yes? 0? No? More than 0? 3. 3 is the right number. So I get an unused variable warning for B, E, and F. I walk you through this. So in case of A, I ask to capture by copy. And the lambda requires to copy a std string. And a std string, if copied, does allocate memory for the new string and copies over from the source to the destination. The compiler is not allowed to optimize this away. It's a so-called side effect. If it would be okay for the compiler to optimize it away, we would have no copies of std strings. But in the moment the compiler copies something there, it is used. B, on the other hand, we say that we like to capture by copy, but we don't use anything, so that's basically an empty lambda. Unused variable warning, just nice and easy. C is equivalent to A. The more interesting part then is D. Because in D, I specifically request foo being captured by copy, but I don't use it. This is one of the cases where the compiler does what I tell it to do. I ask specifically to capture foo by copy, regardless if it is used or not. And if I do so, I do get a copy. So this lambda, even if it doesn't use it, has foo captured inside of it, and that's why it is not optimized away. For E and F, it's easy because they are captured by reference, so the compiler can through to it that it's not used. Why I'm telling you this? Because I've seen code like this, smaller pieces, less lambdas, just a single one, which either is there for debug purposes or you have some if def target something in your code. And the lambda is only, it's globally there, but it's only invoked if the if def triggers. So if it's for debug or for your specific target. And the impression then often is, well, this is that code. It will be optimized away. So I don't have to do anything about this lambda sticking around there. And this impression is wrong because every time you pass this lambda, you will get a copy of that std string. And if that std string would be of size of 100 megabytes or so, then I hope that you can see that it makes a difference of capturing this or not. I once told that to some Windows programmers, and they looked a little bit non-understanding at me, and they said, well, and I said, yeah, isn't that something for you? No, we just asked the customer to buy a bigger PC. Problem solved. So not everybody cares about things like that. Let's talk a little bit about C++ 17. There we have const per lambdas. And with that, they are now usable in const per contexts. And what you can do with them is, like I've shown you, showing you in main. There I have a const per int array called R of size 5. Then I have a const bool, name all 11, and I apply an algorithm to it, all of, which walks through all the elements in my array and applies a lambda to it. And this lambda has to be const per because I'm invoking it in a const per context. And it only checks if it's an even or an odd number and returns it. And then I can return all even, and this whole block in main is now evaluated at compile time, which is very nice. And some of you may now ask, well, and why are you giving me this boilerplate code above of main? I know that there's a std algorithm to do that. And that's exactly the version of the std algorithm from CPP reference. I copied it from there. With one exception, and that's why I have to show it to you in C++ 17. In C++ 17, we got const per lambdas, but unfortunately, the algorithm's header, the functions in there are not const per. So I had to add the const per keyword in front of the two functions here, all of and find if not. With C++ 20, things get better. There we have const per functions in the algorithm's header, so I can remove the boilerplate code, and the example looks like this. In addition, we have const per begin and end functions, so I can now, if you prefer this, use a std array instead of a plain old int array. How can we apply lambdas? This is one example from C++ Insights. There I have multiple places where I have to wrap something in either parens or curlies. Because I'm making initialization, I am printing out a function call or function itself, things like that. And of course, I all the time have to check whether it's a brace or a curly or parentheses. I have to open it, then there is some code which is in between, and then I have to close this thing. With lambdas and templates, I'm now able to have this wrap in parens or curlies function, which just inserts the opening part before invoking the lambda and then closing with the correct matching brace part. This cleaned up the code by a lot, and it made the call side look more beautiful because I have now a more meaningful function to call there, and I just pass in the lambda, which does the actual job. But I reduced the boilerplate code. A variation of this is this example again from C++ Insights. I have to make up argument lists. And argument lists have that thing that the first argument has no comma before it and after it, if it's the only parameter. But the second parameter then has to have a comma before it, but the last one does not have to have a comma after it. So basic rules, writing functions or function calls. To ease that up, I have now this function for each argument, which goes through an argument list and does insert a comma if required. And this once again dropped my call side code by a lot, just by using or applying lambdas here. Another pattern coming, I believe, from JavaScript is the immediately invoked functions expressions. I like this pattern, I use it a lot. This is again an example from C++ Insights. I use it to make more variables const. In this case, I have a variable name which I initialize with a directly invoked lambda, which returns a std string. And that std string is either the name of the class, if it's a normal class, or my own made-up name if it's a lambda. Without the directly invoked lambda, I would have either decide to default initialize name empty or with the class name, because it's the probably more often case, and then my name would not have been const. With that, it can be const. I like these things. Here's another place where lambdas can be very helpful. It's a small code fragment. It imagines a POSIX API. I have my open call there, which returns a file descriptor, which is saved in the variable fd. I then check whether fd is equal to -1. Sorry for the bug in the slide here. Equal to -1. If so, I return 0 because I was not able to read anything. Then I try to read into the buffer up to the buffer size from the file. I once again check if that operation was successful. If not, I return. If so, I truncate the file, I close the file descriptor, and I return the size read. Do you see the bug? It's not? The file is not closed in line 13 when I leave there. It's a common mistake. Current kernels allow you 4096 file descriptors, I believe, so it can take a while until the problem really emerges. We can fix this very easily. In the guideline support library, the GSL, there's a function called finally in it, which uses a class template called final action. And I'm just showing you final action here. So I use final action, the class template here. I make a variable out of it with the name clean, and I pass a lambda into it, which captures by reference, and it does if my file descriptor equals -1 check, and then I have to close the file if it's not equal to -1. Now I can remove the close statement, the remaining close statements from the code, and each and every time I return from this function, my file descriptor will be closed if it is open. And the code behind this is fairly simple. This is the class template called final action. It has one member of type T, maction. In the constructor, it takes the lambda and stores it in the member maction. That's it. And then, if I leave the scope, the destructor is invoked, and it calls the lambda. That's the trick. Very easy. Very, very helpful for cleaning up resources. Let's peek a little bit into C++ 20 and what's coming there. So with C++ 20, we will have lambda capture pack expansions, capture, and apply functions to it. For example, move or forward. So have a look at the invoke later. It's a variadic template function which returns a lambda. And this lambda captures the entire pack named args with using init captures. So inside the lambda, it's called margs. And with C++20, I'm now able to apply stood forward to the args pack coming from the invoke later function. And with that, forwarding my captured variables efficiently. So if it's a std string, as in my case, a temporary, I can now forward and with that move it into the lambda such that I have as less copies as possible. This was not possible before. I could capture packs pre-C++ 20, but I cannot apply the functions to it. We will also have templated lambdas. And let me first make a point why they can be good or where they can be good. So this is C++14 code, generic lambdas. I have the implementation of a max function. It takes two parameters, x and epsilon, and it returns which one of both of them is the greater one. Very easy. I can invoke it as in line 7 and 8 with 2, 3, and as in line 8 with 2, 3.0. I'm fine with the first one. I'm not so fine with the second one. Because in the second one, I'm mixing types. I'm comparing now an int with a float. And there is no easy way in C++ 14 or 17 to say that both variables have to be of the same type. In C++ 20 with templated lambdas, we can now say in the angle brackets that this lambda expects a type named t, and that both my parameters x and epsilon are of type t. So it's now the same thing we would do with a lambda with a usual function template. Now we can apply it to lambdas, which means that the second invocation with 2, 3.0 will now no longer compile because there are no implicit conversion when it comes to templates. We can do other things with the templated lambdas. We can now say that our lambda takes a stud vector of type t. Before that, we can only say it takes auto. But now I can say, okay, this lambda takes a stud vector of any type. And this type t is a template parameter, so it just let the compiler figure it out. But it has to be a stud vector. I can also apply non-type template parameters to it in the example below by saying, okay, my lambda takes a stud array of type int, but I let the compiler deduce the size. It's like templates. And there's one thing. When doing trainings, I have this one exercise where the students get a piece of code, C++ 98 code, and they shall transform it into C++ 11 by applying auto to it. It's just to get a feeling for them if they are new how to work with auto. And the exercise is just apply auto in all the cases where it feels good or looks right for you. And one piece of code is I have a function called square taking an int parameter. And true story, in each and every class I'm doing this, there's at least one person which has in the square function auto, replacing the int by auto. And when I'm seeing this, I ask, does it compile? Yes, yes it does. Then I ask, do you know what you're doing? I applied auto to it. That's right. But which compiler are you using? I'm guessing and betting it's GCC, right? Yes, it's GCC. Have you tried out Clang yet? No? Please. Oh, it doesn't compile anymore. I don't know if it's a feature or a bug, but GCC allows you to have auto everywhere as a function parameter, pre-C++20. I believe it came in as a probably bug with C++14 with generic lambdas when auto is possible in a parameter list of a lambda, and they just didn't restrict it enough. So it's possible in every function, making that function a template, essentially. It's always funny, and this is why this code compiles in GCC in C++14 mode. It can have partially what we will get in C++20, but not that good. We will also have in C++20 default constructible lambdas, which we can use in a decal type expression. And to this day, I'm not really sure if I'm comfortable with that or not. So here's the C++14 version. Assume we have a std map, which is of type std string and int, and we like to have a custom compare function for it. Then what we can do is come up with a lambda, capture it in a variable named compare, and this lambda does the comparison. Then, when declaring the std map, we say it's of type std string and int and decal type compare. That works, of course, it's great. We have also the compare function lingering around without being used anywhere else. And we maybe can like to narrow the scope down a little bit more. And this is possible with C++20 because now we can have our default constructible lambda in the decal type expression directly. So no need to declare a variable before, come up with a name, having that thing lingering around there. No, now we can place it exactly where it belongs to. I like this. I'm not sure how good it is that I now can write hundreds of lines of code in a decal type expression because it's a lambda. But we will see what fun things appear with that. To conclude this a little bit, can we overuse lambdas? Of course. This is my own example coming from C++ Insights. If you look a little bit at this two-liner, you may wonder what sense that lambda makes there. I cannot tell you why it put it there in first place. Either I refactored something or I had something different in mind. But honestly, it's enough to have it with just initializing the bool with the value, because the lambda didn't do anything good. So I don't know what the idea initially was. But yes, we can overuse lambdas, as good as they may be. If you are more interested in lambdas, because the time was too short to tell you everything about them, there are a lot of work of others. It's an incomplete list here. It would fill more than one slide. So there's a Meeting C++ talk from Björn Faller, who appears to be also here, called High Order Functions for Ordinary Developers. It's real great talk if you like to see more how lambdas can be applied to your code and how they still ensure that you have just the tiniest code you can write yourself. There is a blog post, I believe, from Vittorio Romero talking a little bit about compile time iteration with C++20 lambdas. There are a bunch of C++ weekly episodes from Jason Turner, and there's another blog post going through the evolution of lambdas from C++11 to 20. That's it so far from my side. I will be here until Friday, so if you have any questions after that, feel free to reach out to me. I have just 3 more words to say, and that's, I am fertig. Thank you.